In the last module, we gave a brief introduction to convective heat transfer. We classified heat transfer based on external and internal flow. While doing so, we also looked at the definitions of average velocity, bulk mean temperature. We looked at the importance of T mean as opposed to T infinity vis-a-vis internal and external flow. The role of T fluid is taken up by T infinity in external flow, is taken up by T bulk mean in case of internal flow, and T saturated or T sat in case of phase change applications. So, the heat transfer coefficient was defined. We also had local and average values that were talked about. We also went back to a little bit of fluid mechanics, talked about the concept of fully developed flow, hydrodynamically fully developed, where we said that the gradient in the gradient of the velocity in the flow direction is equal to 0 after the entrance length. And just to recap, I will just draw the figure and then we will recap that and then proceed from there. So, if you take a pipe and if flow is coming in at u infinity T infinity, we said that the boundary layers are formed in the pipe, boundary layers merge here, and this location is called the entrance length or entry length. Beyond this point, we said that the temperature, the velocity distribution is kind of parabolic or symmetric about this position, and this is some Z1 at another Z2 in the pipe, you have an identical velocity distribution. So, we said that the profiles are identical. So, if I cut the profile at Z1 and keep it on the profile at Z2, it will exactly overlap, and this is the concept of hydrodynamically fully developed, which gives me this condition mathematically. And this was used quite well in fluid mechanics, quite extensively, and this simplified our problems to a great extent. Now, when we came to heat transfer, we said the same thing does not work very nicely, because you are supplying heat, whether it is a constant heat flux or a constant wall temperature application, you are supplying heat continuously, and the manifestation of the additional heat would be m dot Cp dt m is equal to q double prime pi d dz. This is what we said if you take a control volume, and in this control volume this heat addition always causes an increase in the temperature, that is q double prime pi d by m dot Cp, and this is always greater than 0. So, the bulk mean temperature is progressively increasing along the flow direction. So, if this was T bulk mean, this is going to be T bulk mean plus dTm over a change in the length dz, and therefore, it seems that in case of heat transfer applications, this temperature profile which we would get. So, if we draw this again for a pipe, and let us say this is your thermal boundary layer, you will see what it is with respect to the hydrodynamic boundary layer, and this is u infinity, T infinity is the free stream coming in. I am not drawing all the arrows. So, what we are trying to say is, if we have a temperature profile for this part at Z1, the temperature profile at Z2 would be bigger. That means, this wall temperature Tw1 will be less than Tw2, that is at values at Z2 location. T bulk mean at Z1 would be less than T bulk mean at Z2 given this condition. Wall also will become hot, therefore, will be having a higher temperature, and therefore, you will see this to be the profile would look similar, but this would be a little fatter, and if you go to a further location downstream, you would still get a fatter profile, and something like this you would see. This is Z2, the profile at Z3. This is for heat flux into the fluid. So, the fluid is getting hot. So, from this it appears that there would be nothing like a thermally fully developed, just so we cannot write dTm by dz equal to 0. Here we have dTm by dz is greater than 0. So, such a statement writing dTm by dz equal to 0 is not possible. So, it appears as if the concept of thermally fully developed does not exist. We will see later on that there is a modification to the definition that will happen. The idea of thermally fully developed would be there, it's just that it will not be the fact as simple as this. It will not be the fact that dTm by dz equal to 0. That is not the definition of thermally fully developed. We would have an alternative definition, we will see later on. This is a very important distinction between the heat transfer aspect and the hydrodynamic aspect. We also defined a local heat transfer coefficient H is equal to Q double prime delta T, and we said local means it is specific to that location. So, if I have a flow over a flat plate, the heat transfer coefficient is going to be different at this location versus this location, so on and so forth. And integration of this heat transfer coefficient H bar is the average heat transfer coefficient, would be integration over the local value over the given length L, and this has very great significance. Where to use local value, where to use average value, that is very important. If I am talking of calculation of heat removal or heat coming in at a particular location, at a location, that means specific location. So, this location I want to calculate the heat transfer. So, if I have say electronic component which has several heat dissipating chips here, this is 1, this is 2, and you can see these kind of figures in most textbooks or even literature. Z1, this is at Z2, and if we have u comma u infinity, T infinity is the free stream velocity and the temperature of the free stream fluid, this is Z3, this is Z4. What we are trying to say is, if this is cooled by passing air over this heated plate and there are 4 different heat generating components, the geometry is like flow over a flat plate, and this would be your Z1, Z2, Z3 and Z4, and you can clearly see that along the boundary along the flow direction, the boundary layer thickness is going on increasing. As a result, this is going to affect the heat transfer. We will see how it is going to affect. The boundary layer thickness is increasing. This is the hydrodynamic boundary layer. The thermal boundary layer also will increase this way. Whether it is going to be exactly the same or below this or above this, we don't know at this point of time. But the thermal boundary layer will also increase, and we would see that the heat transfer coefficient Hz1 would be greater than Hz2, greater than Hz3, greater than Hz4. And if I want to calculate Q at Z1, then I have to use the local value, heat transfer coefficient at Z1, okay, in multiplied by T wall at Z1 minus T infinity. This should be my definition. If I want to calculate Q double prime at Z3 local value, heat transfer coefficient at that location, T wall at that location minus T infinity at that location. This is local. This is what? Local heat transfer coefficient. Now, if I want to calculate what is the heat removed from this location to this location. So, over the plate up to Z3. So, from Z equal to 0 to Z equal to Z3, if I want to find out the heat removal, then I have to use H bar between 0 to Z3. That means I should say H bar over this is nothing but 1 over Z3 minus 0. This is the length 0 to Z3 H local d Z. I am using Z as opposed to X. Books will use X. I am using Z on purpose because we are dealing with the flow direction. Many times X refers to quality in multi-phase situations, but it's perfectly fine if we give X also. Okay, so this would be used. So Q over the length Q between 0 Z in Z equal to 0 to Z equal to Z3 is obtained by H bar, which we have calculated here. Then we say T bar T wall minus T infinity. Okay, so we can assume an average constant value of wall temperature. We probably can do that in many situations, because it might be difficult to keep both the heat flux and the wall temperature constant. So, this is a very important difference that one needs to be aware of, where to use local and average values. Now, when I am trying to use the local and average values, I also need to know how these numbers are going to look like. So, various values of heat transfer coefficients are going to be there. Heat transfer coefficients are dependent on the way the heat is being transferred. So, we have not classified things fully. So, I will just do another type of classification. The convection of the type where it is forced by an external mean. So, that is forced convection versus natural convection. Natural convection refers to the situation where the heat transfer is helped, aided by external forced mean, external means. So, you have a fan or a blower which is blowing the air and the flow is made to occur. So, I have this u infinity. When I have this u infinity indicated, that implies it is a forced convection problem. The moment I see a velocity like this, I have to immediately realize that there could be a Reynolds number which is given by rho u infinity x by mu. So, this is for forced convection. Okay. This is very important, because in natural convection, what is natural convection? Where the heat transfer is not caused by any external means. Then how is it caused? So, the delta T, see, remember one thing, heat flux is H delta T. I need to have a driving temperature difference. Delta T should be greater than 0 for any heat transfer to occur. Okay. So, just as for flow to occur, pressure difference has to be there. Similarly, for heat transfer to occur, temperature difference has to be there. This is something you have to convey to the students. Okay. If potential difference is there, current is going to flow. Same way, if pressure difference is there, flow is going to happen. If temperature difference is there, heat transfer is going to happen. If delta T equal to 0, there is no way heat transfer is going to occur. So, what as a instructor you need to do is give them these connects. So, they study fluid mechanics in one semester, completely forget it. Now, when they come to heat transfer, it's a completely new topic is what they think. But there is a strong connection between fluid mechanics and heat transfer, especially in convective heat transfer. And as instructors, we need to give them this connect at every point. We need to tell them what in fluid mechanics is directly used here. How is it going to be related? Do you see an analogy between what we saw in fluid mechanics and heat transfer? This is one analogy. The other analogy was, yesterday we said wall shear stress is equal to mu du by dy, and here we said that the heat transfer coefficient is minus k dt by dy over some reference temperature. Gradient in the velocity at the wall is responsible for the wall shear stress. This is caused by viscosity, correct? The temperature gradient at the wall is responsible for convective heat transfer, and this is caused by the fact that you have no slippage or no slip, thermal no slip condition. So, there you see tau is equal to mu du by dy at the wall, y equal to 0, h is equal to minus k over some delta t dt by dy at y equal to 0. So, if you see the form of these two equations is identical, the form of these two equations is identical. So, gradient in velocity in the flow direction, in the normal direction, gradient in the temperature in the normal direction, this is my y. Okay, so this is another thing which is common to fluid mechanics and heat transfer. Please bring this out to your students. It's very important that they see the connect. These are not two distinct subjects. Transport phenomena is what is studied in many universities abroad and in departments like chemical engineering, where transport of heat, transport of momentum, transport of species, all of them are studied simultaneously. We make it separate and thereby lose the connect between the two. Make sure that this connect is told to the students and they are made to understand that driving temperature difference is needed for heat transfer, just as pressure difference is needed for flow to occur. Okay. So, natural convection, what is happening? How is this flow established? Delta T causes a delta T would be there. This causes a difference in the densities, and this causes the flow to occur. Where do you see this kind of phenomena? So, you might have seen heated plates which would be suspended for cooling. Okay. This is at some high temperature T wall. What happens? The fluid near the air near the wall would become hotter, and therefore it is going to rise up, and this in turn would bring in the cooler air here, and some kind of a current is going to get established. So, this is something that you would see in everyday life. When you keep a saucer with some hot liquid for cooling, this is going to be at T, which is greater than T ambient or T infinity, and the air near the fluid is going to take up the heat, become hotter. So, T greater, density will become smaller. So, higher the temperature implies lower the density. So, this air here would become light. So, it will rise up, it will bring the colder air here, and the process would be established. So, over some time you would cool this liquid quite slowly though, but you definitely cause cooling of this liquid. So, there is a convection current established not by a U infinity or an external fan. The same hot beverage, if you are trying to cool and you want to really cool it fast, you will put it under the fan. That fan is giving you a U infinity, a velocity which will aid the heat transfer. So, obviously common sense and everyday observations tell me that the Q H delta T, the heat removal rate is much slower in case of natural convection as opposed to forced convection, which means given the same delta T, the value of H, see this Q double prime is directly related to the total Q. Okay, Q double prime into area into dt or delta T time is going to give you the total heat transfer. So, in 10 minutes if I say, or in 1 hour, the amount of heat removed in natural convection will be much smaller than what is removed in forced convection. So, this means that the heat transfer coefficient for natural convection obviously is less than the heat transfer coefficient for forced convection. This is very, very important. So, when I see numbers for these heat transfer coefficients, I need to have a feel for what they could refer to. H is equal to 20 watt per meter square Kelvin. What is it? Is it for natural or forced convection? What could the problem be? H is equal to 100. What could the problem be? H is equal to 150. H is equal to 10,000. What could the problem be? So, we will have a feel for these numbers once we get an idea what these numbers will look like. So, if I were to classify this, the heat transfer coefficient for natural convection for gases or air would be the lowest. Then we would have for liquids, this is the lowest of the lot. I am writing them in increasing order of H. H for forced convection, gases, air would be smaller than for liquid. This would be of the order of tens of this kind. I am not giving you exact numbers, something of this kind. This would be for air or gases, it would be like few near 100 and going up to say 400, 500 or so, few hundreds. Okay. Medium. Very high. Phase change or boiling heat transfer is of the order of 10 to the 4 to 10 to the 6 SI unit watt per meter square Kelvin. I am sure this Q double prime is equal to H delta T, sorry, H into delta T. Therefore, H is equal to Q double prime by delta T. The units are watt per meter square divided by Kelvin, which is what it is. So, as teachers, we should be able to tell students what the numbers look like, and if these numbers are seen, they should be able to have a feel that, oh, the heat transfer problem would be one of forced convection. The heat transfer problem could be one of natural convection. This, if it is a forced convection problem and the heat transfer coefficient is like 100 or 80, 90 or something like that, the problem could be involving a gas. Why the thermal conductivity of gases are going to be lower than liquid? And we saw that H minus k dt by dy at y equal to 0 divided by delta T. This k is for the k of the fluid, not of the solid. So, thermal conductivity of the gas being low, the heat transfer coefficient would be low. We also defined local or average Nusselt number. I am just going to write this as HL by K fluid. This quantity Nusselt number is a non-dimensional representation of the heat transfer coefficient. Just as you had Reynolds number, we now have Nusselt number. This has a form similar to Biot number, which we saw in transient conduction. You would have seen this in transient conduction. This is H characteristic length by K fluid. This is H some other characteristic length divided by K solid. These two characteristic lengths are not the same. This is volume by surface area here. This is diameter of the tube or diameter of the sphere, distance along the flow direction x. That could be the characteristic dimension for external flow. Though we write the form to be similar, there is a great deal of physical difference. This is conductive resistance to convective resistance ratio of those quantities here. This has nothing to do with that. This is primarily a non-dimensional heat transfer coefficient, H LC by Kf. If I say H is local, then Nusselt number would be local. So, number these. So, H being local value implies Nusselt number is local, is given by Hx x over Kf. Average over that length is the average value over that length into that length Kf. You replace x by L, you would get for the entire length of the flat plate. Nusselt number, where the characteristic dimension is that of the diameter of the pipe, it is just Hd by Kf. So, these definitions you can introduce to the students right away. Okay. So, now we said that hydrodynamic and thermal boundary layers are formed. Both are formed because of the difference in the velocity at the surface and the free stream, difference in the temperature at the surface and the free stream. We cannot prevent this difference from happening, otherwise there would be no flow, no heat transfer. So, the difference is bound to be there. That causes the layer of the fluid closest to the heated surface. Now, I am going to talk with reference to heat transfer. So, if this is the hot surface, the fluid in contact with this hot surface will become will have the temperature as the surface. So, T fluid is equal to T wall at y equal to 0, no slip thermal, no slip condition. Now, if the fluid is cooler than the wall, then there is going to be heat transfer from the wall to the fluid, and there is going to be progressive reduction in temperature of each layer of the fluid, so that finally there exists a layer whose temperature is equal to T infinity. So, there is going to be a temperature gradient, as you would see, and that is what we have drawn repeatedly. This is the flat plate, a layer of the fluid which is at T wall, next layer something different, it is highly exaggerated. What I am trying to show is the development of this so called thermal boundary layer. So, this point where the temperature almost is equal to T infinity, further this T wall is going to become larger, it is going to take a greater distance in the y direction for the fluid to reach T infinity. Locus of these points, when I join the top portion of these points where fluid is reaching T infinity, I get what is called as a thermal boundary layer. Just as you got your hydrodynamic boundary layer, I get what we call as a thermal boundary layer. This thermal boundary layer and hydrodynamic boundary layer are very, very important from understanding the heat transfer concepts. Delta T is the symbol for thermal boundary layer. Now, flow is happening, u infinity, t infinity is a pair, remember I told you. So, velocity distribution, if I were to draw, it would look something like this. This is what you would think. But that means the thermal boundary layer has the same thickness as the hydrodynamic boundary layer. Is this always true? No. This is not true as a rule. It could be of the same order, meaning they could be almost the same. And who decides this, whether the thermal and the hydrodynamic boundary layer are the same? Why is thermal and hydrodynamic boundary layer formed? Hydrodynamic boundary layer is formed because of viscosity. Viscosity is responsible for transfer of momentum from the surface to the free stream. Free stream means further in the y direction, normal to the plate. Heat transfer is analogous to momentum transfer. Momentum transfer happens because of viscosity. Heat transfer also has the same mechanism, and a fluid property which takes care of that is called what we define as a non-dimensional number, which is called as a Prandtl number, which is given by the formula mu Cp by K. Everything is for the fluid, mu F Cp F divided by Kf. So, this non-dimensional quantity, this is the thermal conductivity of the fluid, this is mu Cp. This decides how effective, how quickly heat is going to get transferred in comparison to how momentum is going to be transferred. Okay, we will see this and more of this in the next module. Thank you.